Hello, students. This is a PowerPoint, a set of notes that's meant to review calculations that we did in the fall semester. We're going to look first at molar masses, and then we're going to look at various conversion problems. Moles to grams, grams to moles, and also the conversions that are possible between the moles and the unit of volume, the liter, and moles and the actual number of atoms or molecules involved in that mole. Now, what is the mole? Well, first and foremost, it's a unit in the metric system. The metric system has actually been set up to use this particular number. And we define this number as the amount of a substance that contains 6.02 times 10 to the 23rd atoms or molecules of that substance. And we often write it 6.02 E23 because that's a convenient way to enter it into a standard calculator. Now, the number itself is sometimes called Avogadro's number. It's named after 19th century Italian scientist Amedeo Avogadro. He didn't come up with the number himself, but he was so famous for his work with gas laws that involves tiny little particles that once this number was determined, they decided to name it after him. It's a very important and it's part of the metric system. We use it all the time in chemistry. And so you must memorize this number, 6.02 times 10 to the 23rd. Now, that number may seem very large and awkward, but it's actually convenient. It's been deliberately chosen by the people who developed the metric system. It's been deliberately used by chemists because it's convenient for our purposes. Just like it's convenient to use the unit like a dozen to count food items like donuts, it's convenient for us to use this very large number to keep track of the very large number of very tiny particles. In practice, this is necessary because it's almost impossible to actually follow individual atoms. Here we have an electron microscope, which is a very large, expensive gadget. And with it, it's actually possible to locate and see faint, fuzzy images of individual atoms. So here in the illustration, we have individual silicon atoms that have been arranged in patterns, and you can see them. You can't actually see them doing anything interesting. They're just sitting there, and they're not interacting with anything else. They're not actually doing chemistry. Actual chemistry typically involves atoms that are in motion, and they're just impossible to follow. It's just not practical. Fortunately, we don't actually have to follow individual atoms. We use relatively simple math techniques to keep track of how many atoms are there. And one of those techniques is the mole, which again is defined as 6.02 times 10 to the 23rd, particles of some substance. It could be atoms, it could be molecules. Sometimes we just say particles, which is a general way to talk about it. So that's the mole, and that means we define the molar mass as the mass in grams of 1 mole of substance. For example, your mole of substance could be an individual element, say an atom of hydrogen. And if you have a mole of hydrogen, it's going to have a certain mass in grams because it has a certain number of protons in the nucleus. If we're looking at a different element that has more protons and neutrons in its nucleus, say like nitrogen, the same number of atoms or molecules will have a different mass in grams. Now, how do we calculate the molar mass? Well, we simply divide the mass of something in grams by the amount of that substance, and it's convenient to express the amount in terms of moles. So we're actually just taking grams per mole. So you just take the number of grams and divide it by the number of moles. That's the molar mass. Now, how do we do it for an individual element? Well, it's very simple. You go to the periodic table, and the periodic table in the boxes for the individual elements will see numbers, and one number is a whole number, which of course is just the atomic number of that particular element. Here we have carbon, which is atomic number 6. But within the box of periodic table, you'll also see a decimal expression. That's the atomic weight of that element. And that number, which is a decimal, is actually given in grams. And we can treat that atomic weight in grams as identical to the molar mass, which is simply grams per mole. If you have 1 mole of carbon, why, you've got about 12.011 grams of carbon. Now, if you're going to try to figure out the molar mass, not of an individual element, but of a molecule that has different kinds of elements, compounds, you may have to do additional steps. For example, let's say we want to calculate the mass of a diatomic gas like hydrogen. Remember, most of the hydrogen in the atmosphere is not hydrogen atoms by itself. It's two hydrogens stuck together, H2, a molecule that has two molecules, or sorry, a molecule rather that has two atoms of hydrogen in it. And so what we have to do is we have to take the atomic weight of hydrogen and multiply it by 2. For every H2 molecule, there's 2 atoms of hydrogen. So we cancel out the atoms of hydrogen, we multiply across, and we see it's 2 times 1.01 grams per mole. And so for H2, for the hydrogen gas that's in the diatomic state, it's not 1.01 grams per mole, it's 2.02 grams per mole of H2. Now, even more challenging, consider the ionic compound calcium nitrate, which has the formula CaNO3 inside parentheses, and then a 2 on the outside of the parentheses. The 3 and the 2 are both subscripts, and they indicate the number of each element that's there. And a subscript outside the parentheses means we have to multiply everything in the parentheses by whatever number is in the subscript. So as an example, we're going to need the mass of 1 calcium here, but we're going to need 2 times 1, 2 nitrogens, and we're going to need 2 times 3, 6 oxygens. Now for the periodic table, calcium is 40.078 grams, nitrogen is 14.007 grams, and oxygen is 15.999 grams. That's the mass of the individual element by itself. But we only need 1 calcium, but we're going to need 2 nitrogens and 6 oxygens. So the numbers for nitrogen and oxygen we have to multiply by 2 and 6 respectively. So we take these numbers, 40.078 plus 2 times 14.007 plus 6 times 15.999. And we add it all together, you see we have our result. We say it's 164.086 grams per mole of calcium nitrate. Now what makes the next part difficult is that in order to do these conversions, grams to moles or moles to grams, you're going to need to get the molar mass first. It takes a certain amount of work to get a molar mass, and the more complex the formula for the substance we're trying to get the molar mass for, the longer it takes to calculate it, the more steps you need. So molar mass is a calculation by itself. But if you're going to convert from grams to moles, or moles to grams, you're going to need that molar mass as a conversion factor. So how does it work? Well, to convert grams to moles for a given element, you're going to divide the given amount of grams by the mass of 1 mole of that element in the periodic table. And when we do that, the grams will cancel, and your answer will be in moles. Suppose we have 67.2 grams of oxygen. That's given. So what do? We take the 67.2 grams of oxygen, we write it as a fraction over 1 inside parentheses. This is for the purpose, eventually, of cancellation. Because in chemistry, we don't just cancel numbers, we cancel out units and substances as we are able. So when we say 67.2 grams of oxygen, 67.2 is the number, the gram is the unit, and oxygen is the substance. And since the grams of oxygen are given, that means we want to actually get rid of the unit and substance grams of oxygen. We want to get our answer in moles. So if we consult the periodic table, the number given for oxygen by itself is 15.999 grams. And so since we have grams of oxygen given in our first expression, we're going to put the grams of oxygen on the bottom of the second expression. And that will allow us to cancel the grams of oxygen. And now it should be fairly obvious that the number on the top, 67.2 times 1, is still 67.2. And the number on the bottom, 1 times 15.999, is still 15.999. So we're simply going to take the non-1, the non-unity number on the top, 67.2, and divide it by the non-unity number, 15.999, on the bottom. When we do that, we get this number. It's actually a long decimal, 4.20026. We round it to 3 significant figures, and we have 4.2 moles of oxygen. Why is it moles of oxygen? Because that's the unit and substance we did not cancel. Let's do another one. Here our given is going to be grams of sulfur, 234.33 grams of sulfur. And again, we write it as a fraction over 1 inside parentheses. Now, since that fraction has grams of sulfur given with it, we want to get rid of the grams of sulfur. And so we go to our periodic table. It tells us that the molar mass of sulfur is 32.06 grams per mole. So again, we position the grams of sulfur on the bottom, which allows us to cancel the grams of sulfur. And then the non-unity number on the top is divided by the non-unity number on the bottom. That is the numbers that aren't 1. 234.33 divided by 32.06 gives us 7.31 moles of sulfur. Now again, it was actually 7.3091, but we're rounding to 3 significant figures. Now, what if we want to reverse it? Instead of going from grams to moles, we want to go from moles to grams. Well, that's even easier, because here, instead of dividing, we're just going to multiply. But notice that we're still going to use the molar mass of that substance as the conversion factor that allows us to cancel one unit and replace it with another. Let's say we have 6 moles of oxygen. So moles of oxygen is given. We write that as a fraction over 1 inside parentheses. Okay, so now we take the molar mass, and instead of having the grams on the bottom and the moles on the top, we flip it. We have 15.999 grams of oxygen on the top, 1 mole of oxygen on the bottom. And since that's the case, we can cancel the moles of oxygen. And this is just going to be multiplication on the top, because we don't care about the ones on the bottom. And we get approximately 96 grams of oxygen. Or with sulfur, we could say that we are given 4.8 moles of sulfur. We write it over 1 as a fraction inside parentheses. We consult our periodic table, and once again, we have grams and we have moles, and again, we put the grams on the top and the moles on the bottom. The moles of sulfur will cancel, and again, everything on the bottom is 1, and so this again is just multiplication. 4.8 times 32.06 gives us 153.89 grams of sulfur. Now, whether grams to moles or moles to grams, the basic principle is always the same. Now, what if we're dealing, though, with a complex substance? Those problems just involve individual elements. Suppose we have multiple atoms of more than one element. Then we must first calculate the molar mass of that substance. And that's the part that makes these things extra challenging, because it's just extra work you have to do before you're ready to solve the problem. But once you've done the extra work, the actual setup is the same. So let's say we're going to have 45 grams of a compound, a molecule, potassium hydroxide. The formula is KOH. Now, KOH means you got 1 K, potassium, 1 O, oxygen, 1 H, hydrogen. They have different numbers in the periodic table. In this case, we only need 1 of each, and so we just add them together. And when we get done adding them, we determine that the molar mass of potassium hydroxide is 56.105 grams per mole, the number shown in red. So that's going to be our conversion factor. Okay, so again, we were given the idea that we have 45 grams of potassium hydroxide, KOH. So we write 45 grams KOH over 1 as a fraction inside parentheses. And so we have grams of KOH as the unit in the substance at the top of the first expression. We've got to have grams of KOH on the bottom of the second. And so we put the 56.105 grams on the bottom, and we put the mole of KOH on the top. Of course, the grams of KOH will cancel, and we're doing division. And since 45 is less than 56, we have a number, a little decimal that's a little bit less than 1, 0.802 moles of KOH. Now notice you had to do the molar mass first. You had to figure out that number, that conversion factor first. But once you had it, the setup and the way you solve the problem is exactly the same as it is for simple elements. And it's always the same procedure. And we can use similar reasoning to convert grams of substances into moles of substances, moles into atoms or molecules, or even grams into atoms or molecules. Now again, we're just going to use Avogadro's number. And the beautiful thing about Avogadro's number, and the reason why you have to memorize it, is because you don't use it just to move moles to grams or grams to moles. You use it for all sorts of things. It's in the very middle. Let's say we want to figure out exactly how many atoms or molecules are involved. Okay, so we have 13 moles of carbon. We want to know, well, about how many atoms is that? Well, we write 13 moles of carbon over 1 as a fraction inside parentheses. And since we have moles of carbon on top of the first expression, we're going to have moles of carbon on the bottom of the next expression. Remember, the mole is just a number, 6.02 times 10 to the 23rd. So if I say 1 mole of carbon, that actually means the same thing as 6.02 times 10 to the 23rd carbon atom. It's just a number. But we set it up like this so that we can cancel the moles of carbon. And now you should be able to see, well, this is actually just multiplication across the top, right? 13 times 6.02 times 10 to the 23rd. And so that's going to be 7.826 times 10 to the 24th atoms of carbon. Now, what makes this tricky for a lot of you is that you're not sure how to enter the very large number, the mole, in your calculator. Well, don't worry about that. We'll show you how to do that over and over again in this course until you never have to think about it again. It will become automatic. It really is the easy way to do it. Let's do another one. This time, instead of a single element, we're going to have a substance, and the substance here will be sodium sulfate. And we're going to say that we have 3 moles of sodium sulfate that has a formula Na2SO4. So we write 3 moles Na2SO4 over 1 inside parentheses. Now, this is not a single element. This is a complex thing, but we still use the same number, the mole, to count them. So if we have a mole of sodium sulfate, that means we're going to end up having a mole of 2 sodiums and 1 sulfur and 4 oxygens. So it's still 6.02 times 10 to the 23rd. So we put the moles of sodium sulfate on the bottom, and we put the number of the mole at the top of sodium sulfate. The moles are going to cancel out, and this just becomes math. 3 times 6.02 times 10 to the 23rd. And we end up with this number, 1.806 times 10 to the 24th molecules of sodium sulfate. Now we can reverse the process as well, or we can extend the process. Suppose we're not given the number of moles, we're just given grams. In practice, it's much easier for us to measure grams on a balance in the laboratory than to try to actually look at some pile of substance and say, well, how many moles do you think it is? And that's not practical. So we can measure the grams, and we use the molar mass to turn it to moles. And then once we know how many moles it is, then we can turn that into the number of carbon atoms. So we set it up like this. Let's say we're given 34 grams of carbon. So we write it as a fraction over 1 inside parentheses. And then our next expression will have the grams of carbon on the bottom and the 1 mole of carbon on the top. And then finally, at the end, we're just going to have the conversion factor that for every 1 mole of carbon, we're going to have 6.02 times 10 to the 23rd atoms. And this is the power of this exercise, because you're always going to use that same large number. Once you have it memorized, you just fill it in. So obviously, the grams of carbon will cancel, and the moles of carbon will also cancel. And now we're ready to calculate. Now the difference is, instead of multiplying or dividing, we have to do both. So first you have to multiply all the non-unity numbers on the top. You have to go 34 times 6.02 times 10 to the 23rd. You can do that number on the top and multiply all that together first. And then you'll divide by the non-unity number on the bottom, 12.01. If you do those steps, you have 1.704 times 10 to the 24th carbon atoms. Why is it carbon atoms? Because that's the unit and the substance that didn't get canceled. We can extend this idea to a compound. Here again, we're going to use sodium sulfate. We're going to say we have 300 grams of sodium sulfate, and we write it over 1 as a fraction inside parentheses like we always do. And we're going to take the molar mass of that substance. And remember, this molar mass was calculated by using the mass of 2 moles of sodium, 1 mole of sulfur, and 4 moles of oxygen, right? If you didn't know that number beforehand, you would have to figure out the molar mass. But since you are given a certain number of grams of sodium sulfate in the first expression, then that means the grams part of the molar mass will go on the bottom, the second expression, and the mole on the top. And then, hey, look at the end. The conversion factor is the same because we're just trying to get it into moles. And so 1 mole on the bottom and 6.02 times 10 to the 23rd on the top. And now we're ready to do cancellation. Grams of sodium sulfate cancel. Moles of sodium sulfate cancel. And then just like before, we need to multiply the non-unity numbers on the top, 300 times 6.02 to the 10 to the 23rd. And then we divide that by the non-unity number on the bottom, 142.08. And then we'll end up with this number, 1.271 times 10 to the 24th molecules of sodium sulfate. So it works exactly the same way. It just looks a little more complicated. Now, these are pretty challenging, and notice that this is definitely something that you don't want to try to do in your head. Many of the other problems beforehand, you could probably say, oh, you multiply here or you divide here, and you can do it in your head. And as long as you're doing it in your head correctly, you can come up with the right answer. Because you don't have to hold a whole bunch of different things in short-term memory. But once we start adding more parentheses, and we're not just going from, say, grams to moles, we're trying to go all the way to something else, at this point, the technique of writing everything out really becomes crucial, because this way you don't have to hold everything all in your head at the same time. You have parts of it laid out in the correct order in front of you. Now, the trick with all of these setups is to cancel out the units you don't want, so that the answer, whatever it is you do want, is always in the unit you do want here. This flow chart here you might want to copy. Grams, leave a space, moles, leave a space, atoms, and you have arrows going up on the left and arrows going down on the right. And notice the neat symmetry of it, how on one side you multiply by the molar mass and divide by Avogadro's number. On the opposite side, when you're going the opposite direction, you divide by the molar mass and you multiply by Avogadro. It's very convenient and very neat and logical, very symmetrical. Now let's turn to a slightly different matter, which is volume. Remember, in the first semester, we looked at gas laws, and we talked about an ideal gas and how it occupied a certain volume in STP. And careful experiments by scientists like Amedeo Avogadro demonstrated that if you have 1 mole of a generalized ideal gas, that it tends to occupy the same volume no matter what kind of gas it is. Doesn't matter if it's hydrogen gas, oxygen, carbon dioxide. At STP, it will tend to occupy a volume of 22.4 liters. Now, this is very convenient because just as it's easier to measure grams on a metric balance than to try to guess at the moles, much easier to measure the volume of a certain amount of gas in liters than to try to measure the moles. All right? So we call this number the molar volume, but it's only true under certain conditions. It's true as what's called STP. Now, what does STP stand for? It stands for standard temperature and pressure. So the standard temperature is the freezing point of water, which you can express either as 0 degrees Celsius or 273 Kelvin. And the standard pressure is usually given in the unit of the atmosphere, and we say 1 atmosphere, which is defined to be the pressure at sea level, more or less. So that's standard temperature and pressure. If you're at those conditions, then you can just assume that a mole of an ideal gas occupies 22.4 liters. That volume is called the molar volume, and we can use it as a conversion factor. And notice, just like we just memorized 6.02 times 10 to the 23rd to move from, moles to molecules, now we're just going to memorize 22.4 liters to move from moles to liters. We'll use the same conversion factor over and over again. So here we have liters of a gas. Let's say we have 7 liters of CO2, and we write it as a fraction as always. And we just take the molar volume and we put the liter part on the bottom, 22.4 liters, and we put the mole part on the top. The liters will cancel. It should be obvious that we're just going to divide. So 7 divided by 22.4 gives us this number, 0.3125 moles of CO2. Or we could extend it. We could go from liters all the way to the number of particles. Let's say that we have 3 liters of hydrogen sulfide gas. This is the awful smelling gas that comes out of rotten eggs. And again, if we're at STP, if we're at standard temperature and pressure, we can use a conversion factor that for every mole of a gas, you have 22.4 liters. So liters of hydrogen sulfide will cancel out. And then moles of hydrogen sulfide will cancel out. So here we're going to have to do multiplication and division. So first 3 times 6.02 times 10 to the 23rd on the top. And then we divide the whole thing by 22.4. And we end up with this number, 8.0625 times 10 to the 22nd molecules of hydrogen sulfide gas. We can also go to grams. We can figure out the number of grams by going liters to moles to grams. The molar mass of hydrogen sulfide is the mass of 2 hydrogens, 2.008, plus the mass of 1 sulfur, 32.06. We add them all together, and it will be 34.08 grams for every mole. So if we're given 5 liters of hydrogen sulfide, we use the molar volume to convert that to moles. The liters cancel. And then we use the equivalence of the mole, cancel that. And we have the molar mass of hydrogen sulfide there at the end, the grams on top. And so we multiply 5 times 34.08, divide the entire thing by 22.4, and we determine we have 7.6 grams of hydrogen sulfide gas. This last problem is much simpler. And the reason it's simpler is because instead of dividing, we simply multiply. So if you're given moles of a gas instead of liters, why you just use the molar volume and you simply multiply across. The moles cancel and your answer will automatically be in liters. To keep all of these calculations using the mole in the right frame of reference, this flowchart may be helpful. Here in the center, we'll put moles. In the pink box, we'll put grams. In the yellow box, we'll put atoms or molecules, particles that is. And then in the blue box at the bottom, we have the volume of a gas in liters. Notice that the orange box is at the center and connected to all the other boxes with double arrows, which means you can go in either direction. And now we simply add the conversion factor you'll need. Of course, for going to atoms and molecules or moles or vice versa, we're going to use Avogadro's number. We're going to use 6.02 times 10 to the 23rd. And if we need to go to grams to moles or moles to grams, we're going to have to use the molar mass. And that's a little more complicated because we have to complicate it. That is, we have to calculate it for every substance. And finally, to go to liters or back to moles, we would use the molar volume, 22.4 liters. So the molar mass problems are arguably a little bit more complicated just because you have to calculate the individual molar masses for a new substance every time. But the other conversion factors, you just have to memorize these numbers. Avogadro's number when you're talking about particles to moles and vice versa, and the molar volume, 22.4 liters per mole, when you're moving from mole to volume or back and forth.